Hello, everyone, and welcome to another episode of the Day Zero podcast. I'm Spectre, with me is Z. In this episode, we have a few Valve issues, so that'll be a nice follow-up to a couple weeks ago when we were hammering on them a bit. We also have some fake Vulns, AWS, and a Qualcomm bug. So first, before we get into those topics, I will mention we'll be going on our summer break soon. May 24th will be our last podcast episode until September 6th. We'll still be doing some streams and some videos going out. Like, we're not going to be stopping content completely. It's just the podcast won't be running during that time. So, just wanted to give you guys a heads up. With that said, though, we can get into some of our topics this week. So, first, we have kind of a fun issue that you spotted, Z.
Yeah, fun and also a little bit old. Apparently the paper behind this was published at the end of last month, so we are a little bit late on it. But yeah, it's insufficient input validation in the Marvin Minsky's 1967 implementation of the Universal Turing Machine. This is a CV. They were issued CV 2021 32471, and I think this is probably one of the oldest Vulns definitely that we've covered. Can you think of anything
I can't think of anything I've seen that's older. No.
No, a good 40, 50, 60 years coming up.
Yeah, no, I think that might that might take the cake.
Yeah, I mean, we're saying Vault. I mean, this is just kind of, I think, a good example of some of the issues with CVs. I mean, they're calling this a arbitrary code execution on, if a user can provide data, which is kind of the point of the Turing machine, the ability to run programs. I kind of saw this and was saying, yep, and I'll just submit one for, Python, the ability to execute arbitrary code if you can provide a file to it.
Yeah, it's like the return of that section that we used to have of like
no
not
CV.
a CVE.
Yeah.
So it's it's cool to revisit that. But
yeah, I mean, this is a little bit it's meant to be humorous. Like, say, he did a paper on the intrinsic propensity for vulnerabilities in computers. They're using this as the example. It's not a long paper. I'm hoping it's not serious. I read it in a very non-serious way, but it's still kind of funny that they got the CV for it.
Yeah, it just seems like a bit of fun. I wouldn't take it too seriously, and it's not like the vulnerabilities we typically cover. But
yeah,
I mean,
not much to say there.
Being able to run arbitrary code, I mean, code bad, basically. All right, so with that, we can move into another kind of fun topic, kind of serious topic, which is detecting and annoying burp users. So, Z, I remember you said something about this reminding you of a DEF CON talk, right? Or a DEF CON workshop? I forget which one it was.
Yeah, DEF CON talk. Back at DEF CON 21, there was a talk, Defense by Numbers, making problems for script kiddies and scanner monkeys.
A little bit about me.
Sorry for the people listening who just heard that. I just opened the video. Yeah, it reminded me a bit of that talk. That talk was focused on like the use of defensive status codes to basically screw with scanners. This topic, not quite the same. It does talk about kind of breaking burp things like the crawler and the active scanner and some of its functionality, being able to break that. So there's a relationship there. In general, I will say, like, your security of, like, your company or whatever should not depend on detecting burp users. This is something you generally don't want to actually be doing, but it is still kind of fun. You could mess with, the pen testers or whatever, whoever's using it, script kiddies who are looking at your production website. You could mess with them a bit. A few interesting ways to detect are not terribly interesting, looking at stuff like if on port 8080, the default port that Burp's going to be listening on, checking the fav icon there. There's a little bit about detecting the TLS man in the middle. So basically loading or trying to make a TLS connection from the JavaScript in the browser. seeing if the issuer is port trigger. Again, you like the last one, you can configure away from that. And it just has a few things like different features that it'll add. Or the Burp browser extension will add event listeners or support for the sometimes compression. Just has a few things that you can detect it based off of. I thought the breaking was a little bit more interesting, notably that apparently internally the Burp crawler uses CSV, which stands for cheese separated values. And apparently, if you end up including a cheese emote within your within an href and a link, that'll end up getting, or it'll screw with the sitemap as it gets added. So you can basically create problems there. Similarly, there's this little S character that's used in the intruder. Gets replaced with an A at some point. So you can detect if Burp's being used that way and kind of break the intruder that way. So just kind of a couple fun tricks there. Again, this is nothing really earth-shattering. It just the thought of doing it to mess with somebody testing is a little bit humorous. On the other... Or one of the last things I will mention, they do also call out doing things like querying. If you end up seeing like a .burp collaborator.net URL, you should try and query those via Tor, maybe on a random delay, just to trick the scanner into thinking it got hit. Adding various scanner expected responses into the comments and things like that. I don't know. It's just generally some fun that you can screw with. Testers with. Like I said, I wouldn't recommend doing this for real, but it is fun to think about nonetheless. Maybe trolling a CTF
users.
Yeah.
I feel like I couldn't tell you when exactly, but I feel like we have tangentially touched on that talk actually before. I feel like we had a topic that was doing something kind of similar with messing. Maybe it was with like HTTP headers or something to try to cause the browser to do the browser would respect it, but a scraper or Burp or whatever wouldn't. I forget exactly what the topic was, but I feel like we have touched on it briefly before. But
yeah, that's actually one of my favorite DEF CON talks. So yeah. I've probably mentioned it before.
Yeah, I think I've checked it out. I don't think I watched the whole thing, but I watched a few minutes of it at some point before. It's one of those fun ideas where it's abusing the discrepancies between like the browser and how the automated scanners work. But like Alizif in chat said, it's kind of counterproductive. It's not something that you should actually do. It's basically STO, which I'm not a huge fan of. So, but the concept of it is cool, even if I don't really like the end goal of how it would be used.
Your security should not depend on something like this.
Yeah, exactly. All right, so we'll get into some more serious topics now. Chrome 90 has dropped, and with it has come control flow enforcement technology support on Windows for the latest CPUs, being Intel 11th Gen and Zen 3 AMD. So we've talked about CET a little bit before on the podcast and shadow stacks. And shadow stacks, for those who don't know, is basically where you have like a clone of the stack that gets verified against or used exclusively for control flow.
Yeah, and specifically a clone of the stack of return values. It doesn't store the other values that would be on the stack.
Yeah. So what that provides for you is some backward edge CFI, right? So if you have like a Stack Overflow or something and you smash a return pointer, you're not going to be able to get code execution because even if you can control kind of get control of the flow, it's going to detect that and it's going to block it. It's going to crash the process or whatever. But yeah, so Chrome has finally shipped support for CET. It is notable though that it's only backward edge. It does not have forward edge CFI, which is extremely notable in a case like a browser because vtables are everywhere and are an extremely common attack vector for getting code execution in browsers. So,
yeah, but I mean, using a ROP chain is also very common. So even if you corrupt that vtable and then you go into a ROP chain, it's still getting blocked at that level then.
That's true.
I mean, they only have backward edge. I don't know if I'm not sure if they have any forward edge, like just at the software layer within Chrome. That I'm not sure about. I don't
believe
think so because I mean it's hard to kind of do that with JIT. That said, like Windows doesn't have support for the forward edge either using CET yet, the hardware version. So because this ends up relying on the Windows implementation to some extent, it ends up, when the exception happens, it hits the operating system who decides whether or not to let the program continue. So without Windows supporting it, they won't be supporting it either.
Yeah. And the other thing I'll mention, you just mentioned JIT. They also note that this won't be enabled in the renderer, since the renderer can already access read, write, execute memory anyway, because it has to be able to do JIT. So I think they said because the renderer would be not straightforward to support CET in, and the fact that it wouldn't really be that useful, they just stated in there that it's not going to be enabled in the renderer. So yeah, I mean they're very clear here about what the mitigation will and won't protect against. It's not going to stop every attack, obviously, but it's just another layer to add in there. And especially in the browser space, we've seen that, especially this year, that it needs it. I mean, how many in the wild Chrome attacks have we covered this year, or at least
how many
seen
have we
this year?
covered? Seen in the last month. We're a bunch dropping there a few weeks ago. But yeah, I appreciated this topic actually a lot, just because they were very realistic about what they're getting out of this and what they already have. They do talk a little bit about CFG, which is Windows forward edge control flow guard, which I mean does exist. I just mentioned how they don't have it, but that's specifically utilizing Intel CET. They do have forward edge, kind of in software layer. But yeah, I mean, they were very realistic about what you're actually getting with this, and I think there's a lot of, I guess, kind of concern, especially after the Windows internal post there, rip ROP, that I believe we talked about on the podcast quite a while back. Especially after that, this is just kind of a bit more, I won't say more sane, because the rip ROP was actually fairly sane, and just the title was a little bit excessive, I think, if you only read that.
Yeah. So overall, I think it's a good move by Chrome. The biggest limiting factor here, though, I think, is the fact that CET is something that not a lot of people have. Not a lot of people have Zen 3 AMDs or 11th gen Intel, especially with the crazy silicon shortage going on. So unless you have one of those newer CPUs, you're not going to be able to really take advantage of this.
Not yet.
Yes, exactly. Going forward, this will be more useful down the line when more people can get access to that hardware. But at the moment, it's not really too much of an issue for attackers. So yeah, just be aware of that it's not the end all be all by any means. All right, so we'll get into some of our exploits of the show. Our first exploit is a rate limit bypass in AWS Cognito, which could allow password reset tokens to be brute forced. The root cause is kind of fun. It's a race condition where you could exceed the limit by just sending multiple concurrent requests. So instead of being limited by the 20 guesses per hour that you're supposed to be, you're actually limited to 1,587 that they measured per hour.
Well, in theory, you could probably go beyond that too. That was the maximum they managed to get through. Yeah. I've said this last time we talked about the race condition web, but I love these vulnerabilities. They're so simple to exploit, and they usually have a fairly reasonable impact. In this case, getting around the rate limit on checking reset codes, so you can check a fair few more than you should be able to. And reset codes generally are not the strongest in terms of the amount of entropy. I think they calculate that they have roughly 20 bits of entropy here. So each hour, they were able to test around 0.16% chance of getting the right code. But yeah, the issue just comes down to we don't have the actual code, but presumably the request comes in, it will increment the rate limit, or it will increment, a counter on how many requests were made. Next request comes in, it goes, hey, is this rate limit too high? If it's not, it'll increment it again, let it go through. If it is, then it'll reject it. So by sending 1,000 requests at once, several of them can pass that check before the rate limit actually gets incremented for everybody. Yeah,
so it's not something where your account is instantly going to be compromised. It is quite a significant jump, though, because like you said, it is a 0.16% chance, where normally it's supposed to be like a 0.00002% chance of being able to brute force it, which is significant because it means it can lead to your account being compromised within 650 hours instead of like 50,000 hours. So, it's still quite a bit of time, but it's not as much as it should be. So, yeah, still a significant issue. It was reported March 22nd, and it was fixed by AWS on April 20th. They say they don't have any evidence that this issue is being actively exploited, which isn't too much of a surprise. But yeah, I just thought I'd throw that in there since they mention it. But yeah, I mean, it's one of those things where it's easy to miss when you're writing it and doing like code review, just forgetting that requests can come in concurrently and not thinking about race conditions in the context of web. So
yeah, it's like I said, easily overlooked, and we see it a lot. A lot of the times, though, it's not terrible. Well, I was just saying how a lot of times you end up coming up with this where it is impactful. There's also a lot of cases where it's not all that impactful. It's like, some random increment that just ends up being a little bit wrong that doesn't actually matter. But there are a lot of cases like this where what's being incremented does matter.
Yeah. And another case that I remember we talked about before was like, I think it was in CTFD, but it was a CTF platform where like you could submit flags multiple times because it didn't mark it as solved.
We didn't know.
Safe way.
We weren't told what CTF platform it was. Just the author just said it was a CTF platform.
Oh, right. Okay, fair enough. I thought it was CTFD for some reason, but yeah, that rings a bell.
The better known one, but yeah, no, the author never attributed it or any of those vulnerabilities.
Yeah, good clarification to add there. But yeah, just a fun issue. All right, so next we have a blog post on an authentication bypass in an ASUS gaming router, because I guess we need RGB on routers now too. So they found a vulnerability when digging into the admin panel exposed on HTTP. They identified a set of circumstances that could lead to a session cookie not being properly validated for the session state. And that's because when they do the auth checking, they do a strcomp comparison for comparing the token against the IFTTT token. So if the device hasn't been configured with that token and it's left null, if you set your token to null, you can force that to evaluate to true. And this is definitely not a new issue. We've covered issues like this before on the podcast or similar issues. There is an additional check on the user agent that you have to pass as well. You have to set it to like an internal service ID string, but they just kind of touch on that in passing. They don't go too in depth on it.
Yeah, they don't even show like the code that checks that. So I don't know, that did stand out to me because they make it clear that there's this requirement to do that, and then they don't show us why there's that requirement at any point. I mean, it's not that unexpected that like a service might be using that. But I'm not sure, because it seems like this functionality, like the reason we're getting it is because it thinks of where IFTTT, or if this and that application, because it's comparing their token. I wouldn't expect IFTTT to be using the ASUS service user agent. Like, that doesn't seem like a reasonable expectation. I'm not even sure if you can control what user agent IFTTT will use. So I wish they would have included that bit of information, because I'm genuinely a bit curious on why it's necessary. Might... Oh, you know what? Now that I'm actually talking about, it might be the case that they do... once you're logged in, they're seeing what user you're authenticated as, and IFTTT, whatever user agent it does use, it might check for that and decide that, well, this is... IFTTT, therefore it only has access to a limited set of functions, whereas if somebody's accessing using the service user agent, it would be like have access to everything. So perhaps something like that, but they don't really clarify why at all.
Yeah, it would have been nice to get some more information on that, but I guess they figured it wasn't really relevant to the issue they were covering, which is fair enough, I guess. But yeah, that allowed you to bypass authentication and perform admin actions on the router. They went into quite a bit of the RE here, since there was no source. A little bit too much, I feel. But if you enjoy the RE, then maybe you'll feel differently on that, and you'll appreciate that aspect of it. ASUS released a firmware update that patched that issue at the end of last month. So yeah, that's how the timeline looks for when it was fixed. I don't think they state exactly when it was reported, so yeah, can't comment too much on that. But yeah, that's how that one worked out. All right, so we have 2 vulnerabilities and a false padding oracle in Azure Functions this week. This is a blog post by Polarply. We'll go through the vulnerabilities first, both of which were accessed through the environment variables, and then we'll get to the false padding oracle. The first is a privilege escalation through the SCM run from package variable, which would be used to download an Azure function package. It also had read-write permissions attached to it in the request, which meant if you could mess with that environment variable, you could get it to overwrite the function package and inject your own code, which you could use to give yourself a persistent backdoor that would run every time the function was invoked.
Well, so you wouldn't need to exactly modify with the environment variable. The environment variable includes that you can kind of see where they censored it out here, the sig equals. So that's the, I guess my highlight didn't quite work there. So that's the SAS, or what is it, like signature, something account. Basically, that's where it's getting the permissions from. It'll sign like that token, and then you can go and access the actual storage for it. So because that token or the SAS is actually scoped to have write permissions, you can replace the file that's going to download. So you don't have to change the environment variable. You can just straight up replace the file that it goes to grab.
Right. Okay.
It works. It's, similar thing with S3 and having the signed request there.
And just since you were talking, I thought I'd look it up. SAS is shared access signature. So yeah, that's what it stands for.
Carrying on from that, so you could backdoor it if you got code execution. That is a somewhat big ask, but I mean, we talk about people getting code execution all the time, so it's not that crazy. It's just, getting code execution in the Azure function.
Yeah. So the second bug was through a different environment variable, which was the container start context SAS URL, which contained the encrypted context for the configuration that initialized that Azure function. So by pulling out the SAS token from that URL, they were able to list other Azure function configurations that they didn't own. Though that was limited in impact because it was an encrypted context. You would need the AES key to be able to get the plain text anyway. And that's kind of where the false padding oracle comes into play, because there was a public endpoint on the mesh HTTP server which contained an auth token field in the HTTP headers. And if you sent a malformed token, it would give you an error message and tell you if the padding was incorrect. And it would try to decrypt that header using the same key used for the container context, as far as I understand. So they tried to abuse that to chain with the previous issue in order to get like a full info leak. Sadly, though, they couldn't get it to work. And after looking at the binary that ran the web server, they discovered that the code for performing the unpadding was actually broken or just incomplete. So because of that, it was kind of like the two negatives made a positive, as they said in the blog post. The one bug canceled the other bug out, and that padding oracle ended up not being useful. So
yeah, I really wish it would have landed, because this is one of those bugs that, like, if that would have worked out, this would just be a really awesome chain. That said, I do kind of wonder if the decision, if this unpad implementation was deliberate in terms of how they didn't implement everything, just so it wouldn't be vulnerable to a padding oracle attack.
Yeah, I was looking at their implementation compared to what they said it normally should be, and it was a bit strange that they would do it like that. So yeah, I don't know if that was deliberate or not, because I was kind of thinking in my head.
They don't state if it's deliberate or not. We don't actually know that. It's just they don't actually do the checking for each byte. They just kind of shortcut it, basically.
Yeah. So if it wasn't deliberate, then Microsoft got really lucky here, and the researcher got really unlucky. Like, I feel so bad, because I would be kind of upset if I found such a cool avenue and it was like this weird random thing that you would never expect just completely tanks your chain. So yeah, really unfortunate for the researcher.
It is kind of also, I will call out, having overly verbose error messages, it's one of those things that gets reported that it's often just overlooked. And even though it didn't work out in this case, it's a good example of why those error messages, why you shouldn't have excessive error messages. Like, you should just have like an error code or some minimal information for an attacker, rather than like sharing an actual exception or a stack trace or something like in this case. Because it can disclose a lot of information that you might not expect, as was the case here. Even though it didn't work out, it's still, I think, a good example of why it kind of matters to censor your error messages.
Yeah, for sure. All right, so we have a post on hacking Google App Engine, anatomy of a Java bytecode exploit. So this is a extremely long post that goes into a lot of background. So we're not going to be covering everything. In fact, I think you can skip quite a few of the background info if you wanted to get just straight to the issues, which is probably what I think that's what you did, Z. I know it's pretty much impossible to read all of this in one sitting.
Yeah, but, so, I mean, it covers, like, it starts off covering a bug that it doesn't actually end up needing to use. Still a really cool bug. I'll touch on that in a moment. Then it gets into the actual bug. And then most of the document is actually about crafting the final bytecode. And there are some issues that he runs into with doing that. Just, there's a lot of detail and a lot of methodology. A ton of information in there. We're only going to cover the core of it, but actually, before we do that, I do want to touch on one thing from LM on PC. I just mentioned in chat, and this is related to our last topic. Silencing the error sounds like security through obscurity. Fair point. I haven't really considered that. The security of your application, again, I will argue, should not depend upon simply the fact that you don't disclose error messages. But that doesn't mean that obscurity is a bad thing. It just, like, you shouldn't have your security depend upon it.
It shouldn't be your only line of defense. Like, it's not that it's bad. It's just that you should have other things with it. That's all.
Yeah, and that's kind of what I was saying earlier too. Like, with the burp topic, your security shouldn't depend on blocking burp users or detecting burp users. If you wanted to do that, that's really annoying, and it's actually probably hindering the actual testers who might be using it. But technically speaking, it is adding a little bit, not very much, but it is adding a little bit of security. Similar here, by not disclosing error messages and giving a more actual human error message, perhaps, you might actually be improving the user experience because they don't care that it's bad padding. They're not going to know what that is if they see that, but it does help an attacker. So, I mean, I'd say, like, yeah, your security shouldn't only be dependent on that obscurity. But it is something that there is benefit to some obscurity, I guess. It's not, I don't think it's like obscurity is completely useless when it comes to security. All right, so jumping back onto hacking Google App Engine. Said long post, a lot of details in there. I'm going to focus just on the vulnerability. But the first vulnerability that ends up being covered, which I thought was kind of interesting to at least talk about, ended up taking advantage of the fact that, actually, I guess some context I should get into first. With App Engine, it would perform, you could upload your Java class files, it could execute them, and it would rewrite the class files using this ASM library. So I'm going to be referring to ASM, I'm referring to that library and not normal assembly. It would implement certain checks. So in Java, you've got classes like the reflection class, or you've got class loaders to do custom class loaders and assign permissions. With those classes, you can ultimately get code execution through them. So obviously, they're letting you run some Java, but they're not wanting you to just be able to run arbitrary code within App Engine and like outside of their own little sandboxing. So the way they went about doing that without restricting the actual authors of any of the App Engine applications is to implement kind of a runtime instrumentation So they would add in some extra security checks. So if you use the reflection class, like it would add in checks to make sure you weren't trying to access any of the dangerous functions at runtime. And the way they did that was using this ASM library I mentioned. It would parse the JVM, or it would parse the class file, parse the bytecode, and inject it where necessary. So the vulnerability that they end up finding, the first one that they end up finding, which I just thought was interesting, was that normally in a normal class file, you would kind of have your stack, locals, and code length fields as part of this code attribute, and they would have a length 2 bytes, 2 bytes, and 4 bytes respectively. And in very early Java class files, this is before version 1.02, which was the first stable Java, the sizes were actually just 1 byte, 1 byte, and 2 bytes respectively. So you could end up creating a class file which effectively would get treated inappropriately because most things weren't really aware of that version 45.3. For whatever reason, Java 1.2, the bytecode version that's included in the class file was 45.3. No idea why that is. Probably some history reason. It's not really included in here, and I don't know it offhand. But you could basically take advantage of the fact that the sizes were different to craft a bytecode that the JVM would parse one way, but ASM, when it was doing the rewriting, would parse another way, so you can have different bytecode. They actually link, I believe, to a CrackMe that actually took advantage of that issue, which you can check out. It's just linked in the post itself. I won't add it to the description. But that's kind of the first issue. They didn't use it because in doing that code injection, the App Engine would automatically set the version to 49 as your minimum version. So we couldn't really take advantage of the difference in parsing. I still thought it was a really cool vulnerability worth kind of reading up. The actual vulnerability that they used had to do with how strings were stored, and specifically the string length. When ASM was reading the strings, reads the string, writes them out as like the Java string. Java strings, you get 2 bytes that go to the length, and then that many bytes of actual data. Not really a crazy structure, prepending the size, so you always have it, and not needing a null terminator, so you can actually include nulls in the string. Including nulls in the string, they used MUTF-8 encoding, which I wasn't familiar with. Apparently it does a couple things. Most important here is the fact that nulls are actually rewritten as a 2-byte sequence. So it doesn't actually include nulls in the string itself or in the file itself. And that can just allow some other functions to work. So getting back on the size, what was wrong with ASM is it didn't actually check for any overflowing in the strings. So if you can make it think that you had a 65,536 byte string, because that just overflows into your third byte of size, it'll truncate the first byte and it'll just write 0 as the actual size. Which of course in JVM, when it's parsing sees 0, it's like, oh, the string is done immediately, and starts parsing the data of the string as more bytecode, allowing you to inject bytecode that ASM won't see. So it won't be able to add its instrumentation into it. The challenge ended up being how to actually provide a class file that ASM could read, but that JVM couldn't. Or sorry, I don't know why I said that. That ASM would read and have that wrong size, because obviously that's too large for an actual class file, so it couldn't actually exist. So it took advantage of that MUTF-8 that I mentioned, where ASM would actually accept strings that had the null bytes, and it would just rewrite them into the 2-byte replacement, whereas JVM just wouldn't accept that at all. So because of that difference, they're able to craft a string that has one of those null bytes in it to get it just over the size, to make it think the size is, to wrap around the size or overflow the size by including the null bytes. So that allowed them to effectively inject, depending on the number of null bytes, as many bytes of bytecode as they wanted. From there, the rest of this just basically went into actually building up the exploit, or building up the bytecode that would work. And like I said, a lot of difficulties with that, but on a whole, fairly interesting.
Yeah, it's a really cool attack. In a way, like, I know it's not exactly like it, but the attack complexity kind of reminds me of like the JIT-based bugs that we cover in browsers sometimes. In the way that there's a lot of background information, there's a lot of complexity into how it works and how you exploit it and what the vulnerability even is. But there's like so much background information here that if you wanted to learn a little bit about that area, then you can, right? There's such a breadth of information.
Unfortunately, I don't think I mentioned this. I should have at the start, but this is from 2013. So this is old. Like, this isn't something that's still relevant. Kind of indicates that ASM checks the size now. Java has obviously changed quite a bit since 2013.
So the vulnerabilities from 2013, but the write-up is from
the write-up is new.
Okay, I just wanted to clarify that to make sure.
Yeah,
that's interesting. You don't know. It's not too often you see people go back and write up stuff that's that old, but
yeah. Well, he mentions that he kind of sat on it for a while. This was apparently he was an intern at Google, and just during the last week of his internship, he was allowed to try and attack App Engine, which is where he ended up doing a lot of this. He mentions that he kind of recreated the code. This isn't the original code. Obvious thing being App Engine is kind of a web app, whereas he writes it using like main and stuff. He actually touches on those differences, kind of get ahead of him. On a whole, though, like I said, a lot of background in here. Like I said, very long, hard to actually cover all of it. But like on a whole, the vulnerability is just mess up in calculating in accepting basically the wrong type of strings and rewriting it, leading to that size overflow. Like, it is kind of a simple thing to understand. You just kind of need to understand all these background components in order to get why that matters.
All the context, yeah. Yeah, I mean, that's the only thing that kind of sucks about this blog post, is that it's so long that as soon as you see that scroll bar, it is really intimidating. It's kind of like some of those longer P0 posts we've covered, although this is even longer than those, I think. So yeah, I mean, it's a very long read. I couldn't read it all in one sitting for sure, but yeah, I mean, there's a lot there for anybody who's interested. And the links, we always keep the links in the description for anybody who wants to go into the background info, even though we don't cover that here on the podcast.
Yeah, and I guess I will mention the remediation here was that the App Engine basically just altered the system. So after it ran ASM, it would run it again on its own output to check for those discrepancies. So eliminating the entire class of issue.
Yeah. Up next, we have a bug in a Facebook product called Workplace, which is like Facebook, but for enterprise, which I'd never heard of until this topic. I don't know if you had, Z, but yeah, it was kind of
a couple times. Never used it.
Yeah. So pretty quick and straightforward issue. Workplace has a feature called self-invite, where if it's enabled, it allows anyone with a company email or a whitelisted email to join. Problem is, though, the validation on whether or not the domain is allowed was not actually enforced on the server side for whatever reason. So by just capturing and changing the request, you could substitute the email in for a non-verified one, then join the Workplace.
Yeah, so that it stood out to me here. So the way he goes about actually doing this is he takes a normal request for the invite and then changes the community ID to another community. So it's not said. Like, I read this and I think it just never bothered verifying that email at all. But my guess, because of how he went about this, and needing to intercept the request from like a good invite or more from an actual workplace, rather than just being able to apply directly to the other ones, I would guess there was another server-side check that just happened in another request, rather than it just being the fact that it never does it. It doesn't do it on the actual account's self-invite endpoint, or like when it's actually creating the endpoint.
Yeah, so a bit strange. It is worth noting, given the wording of the article, it seems that this self-invite feature is not enabled by default. It's something that you have to turn on in your organization or whatever. So,
although for the few companies I do know of that were using Workplace did have it on. That said, that's anecdotal. That's just my personal experience.
So I think that's fair to add, because when I was reading that and I read that it wasn't enabled by default, I was thinking the bounty payout gets really surprising when you factor that in, because they paid out 27.5K for this bug. It was a $25,000 payout with a 2.5K bonus, which is awesome for the researcher, but that really caught me off guard given the fact that it's not something that's enabled by default. So I'm guessing it's something that, even though it's not enabled by default, since it's used so much, it didn't really matter, I guess. But yeah, that struck me as a little bit odd, but with that anecdote put in there, it kind of makes sense if I take it to mean that most people just use it, so it might as well be default, basically.
Yeah, I mean, we don't really get information on how they decide the payout.
Yeah, we're completely in speculation town there, but yeah, I mean, we visit there sometimes because we just can't get all the information. But
yeah, I guess part of it, though, they do mention. I'm actually just reading the Facebook thing to see if there's something new. It would have allowed a malicious user to access company's workplace environment via that invite. I guess the other thing was you did need to know the community ID, which he did find an endpoint that would allow you to find that, but at the time of the report, he didn't have that, or at least the initial report. But yeah, I guess even reading the Facebook response here, it doesn't really include very much besides the fact that he had a bonus on there for being in the gold league of their Hacker Plus program, which was just $2,500. So doesn't explain the whole bounty. I assume it's just because it is a full, you do ultimately get full access to the workplace, which you should not have.
Like I said, it is an awesome payout amount for the researcher, and that's one thing that's cool to see with covering the Facebook issues, is the fact that their payouts are really good generally. So, I mean, Facebook is, I think they might be the highest paying company I've seen when it comes to web issues that we cover a lot on the show. So, yeah, the payouts amount isn't
Google
too surprising.
pays out good too.
Yeah, Google's another one. But yeah, I mean, the payout amount isn't too surprising on its own. It's just that aspect of it not being on by default. But whatever, that's by the by. All right, so we'll get into a post from a friend this week on this week's episode, and it is also our first Valve issue in Source Engine that recently got disclosed. So those on our server who have the 0 Day Fans feed or go to the website or whatever might have noticed there were 5 Source Engine reports that were disclosed last week. Valve went on a rush to fix a bunch of issues, I guess because of the public pressure, which honestly I didn't think they would respond to. But
in fact, there was even just one more disclosed 15 minutes before we started the podcast.
Awesome. But yeah, so there's been a lot of stuff that's been disclosed. Researchers are able to talk about stuff they've been sitting on for a while. And yeah, our friend here was also able to write a blog post about it. So yeah, in this post, GBPS talks about some background with Source Engine, as well as using Frida for testing on both the client and server side. I won't go into that here, but it's definitely a good read that you should check out if you're looking at Frida for other projects, or you're just interested in what Frida could be used for. But yeah,
I mean, Frida is an insanely useful tool. I'm actually surprised that he's only associated more with mobile, because I've used it a couple times on mobile, but I've mostly used it actually for Windows apps. So yeah, just different backgrounds.
It's funny how much Frida is used in the mobile space, though, compared to everywhere else. But yeah, so he goes into detail on 2 vulnerabilities he discovered and exploited in Source Engine. Both vulnerabilities were out-of-bounds writes. The first out-of-bounds reads, not writes. The first out-of-bounds read can allow you to get an arbitrary pointer to an iClient networkable object, and that's because they have a not properly checked user-provided index into the global table of them. Basically, I think they check it's an integer truncation issue. So it'll take the lower 32 bits and check those, but it won't check the upper 32 bits, and it's a full 64-bit index. So because of that bad check, which is apparently fairly common across multiple message handlers for Source Engine,
and
you can kind of get around that check.
Yeah, so I think the very first one, like getting that network, what was it, iClient networkable, that one just had a couple of certs that end up getting compiled out. So it did check the max number, and it did check to make sure it was greater than 0. But since they're in asserts, in production builds, it didn't include that. I think what you were getting into is the second one that had.
Actually, yeah, you're right. Sorry. I did get them confused between the first and second issue. This one was just a straight up text one.
Yeah.
So it's a little bit more of a meme issue. So yeah, I mean, it basically allows you to craft a pointer, and you can fake an iClient networkable object anywhere that you can, like if you can set up any data that you control on the heap or the stack, whatever, and you can get a pointer to there, you can craft a fake object, which means you can get code execution because that object has a vtable inside of it. And you can set up fake objects with server set convars. That on its own, though, couldn't be full chained because there is ASLR in play, so there wasn't info leak needed, and you also needed, like, even if you could use a non-ASLR module, and I think CSGO has one, Xinput, you do still need an info leak because there's multiple layers of indirection, because you have to be able to fake vtable too, and be able to find where that's located. So yeah, that's where the second bug comes into play, which is the info leak.
It sounded like actually the convars were stored in static global, and he made it sound like the location of that wasn't too variable. So he could have used the X input if he wanted to, but only didn't because he touches on it when he gets to the ROP bit. Could have gone about using xinput.dll, but didn't because he wanted this to work on all source games. But it does seem like he's got a fairly reasonable place to access to actually set up that variable, and we'll know where it's located. Like, it seems like it's fairly consistent.
So he did state that he wanted it to work on like both CSGO and TF2 and whatnot. That said, when I talked to him a little bit, I think he mentioned that he still needed an info leak regardless for that bug, even if he just wanted to target CSGO.
Okay, then I misread that.
Yeah, no worries. So yeah, that's where the info leak comes into play. It's a parsing bug when parsing the size of a zip file when it gets uploaded to a server. The variable used for tracking the size is a signed integer, and the size check is a size to compare, so you can kind of guess where that's going. By setting a negative size, you can get out-of-bounds stack contents sent to the server. Now, it is a little bit weird when it comes to how that attack works, because it's not an intended behavior. Z and I were actually a little bit at odds before we started at like exactly what's going on here, because there's kind of zipception happening here. Because basically, when you connect to a server in CSGO, like a surf server or whatever, you get a map file sent to you. And that map file can contain a bunch of different stuff, including its own zip files inside of it, which are pack files that contain game assets. Now, this info leak was vectored through the pack files that are inside of the map file. So there's a little bit of inception going on there with like levels of embedded files, I guess. But
I mean, I don't know what the structure of the actual map files are. Like, I mean, zip makes sense. I don't see anything, but he makes mention that the pack files are used as basically an overlay, where you provide the pack file, and when it looks up, like if it needs to grab some file to load like a texture, it'll look and see if it's in the pack file first. If it's there, it returns it from there, rather than giving the original version of it. So I assume it's being used to like overwrite assets that are provided by like CSGO or by the game itself that could be used, or that are on like the original map. And then the pack file just kind of overlays an original map. I'm not exactly sure how the map system works. That said, the actual attack is in that pack file, where you can have the server can ask the client to upload a file, and it will actually, even though it's getting that pack file or the client's getting that pack file from the server, if the server asks for a file that exists inside the pack file, it still respects that pack file and still sends it out from there, which is why it seems like a little bit of a weird practice, since, I mean, the server knows what it's sending out, or should know what it's sent out. But regardless, when it's reading that, it's going to do the size compare to see, like, hey, is this file too big for me to even send? Like, doesn't want to send, anything more than whatever size. As Spectre just said, does that as a signed comparison. So you can get it to, or you set a negative size in the pack file, and it'll try and it'll think it's less than the expected size. So when it goes to read it, it'll read, like the 4 gigabytes or whatever. I believe this is 32-bit. So it'll read out the whole 4 gigabytes, like off the stack or wherever. And that will give you, your information leak that you need.
And a very good one at that. So
a lot of things are leaked there.
Yeah. So, very interesting exploit. Info leaking in games is the biggest challenge. I don't know how much we've really talked about it because we haven't been able to talk about Source Engine, where Valve was sitting on the bugs for so long. But the biggest challenge of Source Engine isn't really finding memory corruption bugs, because Source Engine's very old. It goes back to like the 2000s. You can find a lot of memeable issues in it, and even issues that you could take to code execution. The problem is the fact that ASLR is in play means that you have to be able to bypass ASLR, and info leaking is just, it's so difficult to do in games because most of the bugs you're going to find are going to be parsing bugs. So your info leak vectors are very limited. So it's something that kind of kills source attacks more often than not, I guess, unless you put in the effort to really try to find those info leaks. So it's cool to be able to talk about one where they're kind of rare in that regard. So I mean, the exploit is cool, but the Frida and setup background information here is what I think I found the most interesting personally. Just thinking about how that could be applied to other targets and whatnot. I think that little background excerpt, it wasn't super long, but the bit that's there, I think, was kind of a good advertisement for Frida in a good way. You know what I mean? It was kind of pushing Frida into why it can be useful and why people should start taking advantage of it. So, yeah, I think that was what I found the most interesting personally from the article. But yeah, overall, just a really good read all the way through. Anybody who is interested in binary exploitation and Source Engine specifically, it's a great post for that, because most of the Valve issues that we've seen have just been the HackerOne reports, and sometimes we don't even get the actual report details. We get like a summary. So yeah, I haven't really seen any blog posts on Source Engine. GBPS is the only person I've seen who's done that. And I will quickly shout out as well, he does have this is a part 2. He has done a previous post on Source Engine before as well. I think it was posted in 2019. So there's another thing you could read too if you were interested.
If you read that, you've read his entire blog. He has 2 posts.
Yeah, lots of posts, but they're very good posts. He's kind of going for that quality over quantity. So yeah, with that said, we'll move into our next Valve issue, which is a HackerOne report. This is a submission from SlidyBat, which is another out-of-bounds read in Source Engine. This is what I kind of got confused with the last report. This is the report where they discovered an anti-pattern where the entity indexes, they check the lower 32 bits, but not the upper 32 bits. And that's because of the integer truncation issue. They're just storing the unsigned long or unsigned long into an integer. So when they do that check, it's kind of pointless because it's not, because if the attacker only sets those lower 32 bits, it can still block it, but it can be walked around.
Don't know what you're talking about. So what I see here in this bug, and I mean, maybe you can go ahead and explain what I'm missing here. They're grabbing the message entity index, line 5, and then they check the lower bound of it. Is it greater than 0? And then they access it. So you can access, if you provide any number larger than 0 and larger than the number in the array, you can access it. Like, I don't see any truncation happening here. It's just the fact that they don't check if it's less than 0 and they're using a signed integer.
Okay, so let me just look at the code really quick, because I was under the impression that they were using a full 64-bit size, or index, sorry, and they were only checking the lower bits. So I need to reconfirm here then.
Unless that's in some of the comments, I only read the report.
Yeah, sorry, I'm just trying to look really quick. Okay. Okay, maybe I was getting that confused with a different report that we dropped, maybe, or something. I'm
The
not
dropped
sure.
one wasn't that either. So I'm legitimately not sure what you're talking about.
Maybe I'm just crazy. It's probably what it is.
Maybe okay. You're talking about your own O-Day.
Maybe I found an O-Day and I just dropped it on stream. No. Okay, so sorry, you're right. This is another like signedness issue. So yeah, I thought they had a problem with the. Okay, whatever. I must just be wild. All right, so yeah, the issue is actually what Z pointed out, is the fact that the index is signed and they just kind of use it there. And they try to do the zero check, but obviously because it's signed, that's not really going to help you there. You can access negative indexes into the array.
Well, so because they check that, you can't access a negative index into the array. But you can access beyond the end of the array. Like, it doesn't check the upper end of the bound.
Yeah. So in the report, they abuse the glow prop turnoff message. They state that this problem exists in other messages too, though. So very much like GBPS's exploit, this can be used to craft a fake object in the entity cache. And again, this has a vtable that they can fake to get code execution when getting the base entity. This report does get a little bit weird when it comes to the info leak. So yeah, for those who don't know the specifics around Valve's bounty program, because of what I stated earlier, with memory corruption being so much more common than the info leaks, a couple of years ago, Valve stopped talking about memory corruption issues, and they would just stop like accepting them. They would just be like, "Yep, we don't care, close." You had to submit a full chain with an ASLR defeat. So that's kind of what happened in this issue. They're like, "We're not going to accept this unless you can full chain it." So the researcher did eventually go and find an info leak and report it. Can't talk too much on that though, because that info leak report is private. So yeah, can't talk too much on that. It is a bit weird though, because the info leak required the client to enable the SV uploads parameter, which is quite a big stipulation because that variable is not enabled by default. So the info leak wouldn't be able to work unless the client had set that themselves. Or set like some other variable that was kind of tied to it. Like I think SV cheats might have been tied to it. But anyway, they did get paid out by Valve. It took over a year for this issue to be resolved. The issue was reported February 29th, and the info leak was found about 10 months ago. February 29th of 2020, by the way. It was then reported to Valve and by the HackerOne triage team 6 months ago, and then it was fixed by Valve a few months ago in the beta branch. We've already criticized Valve on the response times there, so I'm not going to go too much into that. They did get the full $7,500 payout, though, which is now the max for critical issues. It used to be $15K, but they've changed it down to $7.5. Yeah, so it's funny because a couple weeks ago, I kind of mentioned this at the start of the last topic, but we were talking about Valve, and we were kind of hard on them. We were hammering on them quite a bit. I personally said that like there was some pressure from like Secret Club to get these issues fixed. They had an issue that was unfixed for over 2 years. And I was kind of thinking like Valve has never really cared that much about the PR angle. They've always kind of just kept it as like a thing in the background and just tuned it out. So I really didn't think they would care about these vulnerabilities and getting them fixed. I thought it was just going to keep going on, being in the bad state that it was in. But I mean, honestly, obviously I was wrong.
We don't know what Valve is going to continue to do. They might have done this because they were getting heat for it, and we don't know if they're going to continue to do it. You know, their history is that they're going to ignore them. It can be hopeful. I mean, it's a positive step. It's a good reaction, but we do need to see it continue.
Yeah, don't want to go too heavy on praising Valve, because like you said, we got to see how it goes in the future. These did seem very rushed. I mean, like I said, we saw, I think, 5 or 6 different Valve reports that were all fixed. in like a week.
So I actually checked. I think we had 8 hit O-Day fans, and then there were actually even more than that just on Valve, because O-Day fans only reports like high and critical.
Yeah, so Valve went crazy fixing issues. They went on a spree.
And they're still going. Like, so there was one just 15 minutes before the podcast, and even with that one, it's from 2019, so they've still got quite a backlog.
Yeah, so I sent a tweet out saying, we do have to give Valve some credit where it's due. At least they did fix these issues that have been sitting in the backlog. Like you said, though, we got to see how that continues into the future. I don't hold out too much optimism, honestly, because the way that things work at Valve is people just work on what they want to work on for the most part. So it's kind of like if somebody doesn't feel like fixing issues, then they're just not going to get fixed. So, yeah, I mean, I don't hold out too much optimism, but that said, we'll only be able to tell.
We'll see. I mean,
looking at future holds.
It's a positive step. I don't want to take that away from them. It's a good step. I just have questions over if they're going to keep doing it.
Yeah, Phil Cat from chat says maybe there's a new hire at Valve who's got a new company excitement. I mean, that could be true. Maybe they just hired a security person and they were enthusiastically going at it. That's fun to picture in my head. But yeah, I mean, obviously we're kind of in speculation land on what's going to happen with that. All right, so we have a checkpoint post this week on Qualcomm's mobile station modem SoCs, specifically focusing on Qualcomm MSM interface, which is used for Android. A lot of the post is background on QMI and the services that are provided on the protocol stack on the Pixel 4 is what they use for the article. So things like the network access service, the authentication service, the voice service, and there's like a bunch of other ones too. And they also went into some detail about how they fuzz that interface. Basically, they identified the handler routines for the various messages used for RPC, and then they reversed the related structures, stuff like that. Then they used QEMU hexagon to emulate the modem and used AFL to fuzz the interface. I thought that setup was kind of neat and was definitely worth covering in their blog post. Near the end, they talk about one of the vulnerabilities they discovered with that fuzzer that they set up, being a heap overflow in the voice service. The voice service is call config rec handler, I believe. I just want to double check to confirm that. Yeah. So 2 of the fields that are taken from that message are the number of calls to make, which are taken as 1 byte, and then an array of call contexts, which are hex 160 bytes per call. The problem is you can just provide an arbitrary number of calls. There's no checking to limit how many calls you can invoke. They don't seem to state exactly how many you should be able to invoke, just the fact that you can invoke like up to 255 of them if you wanted to. So because it goes to operate on the call context attached to that call, which is usually adjacent in memory, it ends up accessing like way out of bounds and can smash areas of the heap. So because of how you can control how far out of bounds you write, as well as the contents written, this is a pretty powerful heap corruption. Now, at first I was thinking it's very likely you could take this to code execution. They don't really demonstrate that. They just stop at the crash, by the way. But I don't know. It is a little bit hard to say because you are smashing quite a bit of data, like hex 160 bytes. I think you probably could take it to code execution, but I don't want to say for sure because I don't know all the context around the issue, right? So it's hard to speculate. They do note that QMI is protected behind privileges, so it's not like you could just hit it from the Chrome sandbox or even untrusted users. You can hit it from some of the more trusted services, like the media service, for example. So it's still, it's definitely still an issue, and it is viable for privilege escalation, but it is kind of mitigated by the fact that it is behind at least some privileges. So just wanted to mention that. In terms of timeline, bug was reported October 8th and fixed sometime in February. Mostly, the bug here is pretty boring, and we don't have too many details on it. Like I said, they just stopped at the crash and didn't really go any further. I think the takeaway from the blog post, though, is probably the setup. Like I said, I thought that was neat, using QEMU to virtualize the modem and then setting up a fuzzing setup on that. So, yeah, I mean, I have kind of a soft spot for getting some background information on those types of setups. So that's what I found the most enjoyable. But yeah, I mean, Qualcomm. The other thing that's cool about this is Qualcomm is used a lot. It's pretty much used by every Android device in North America, as far as I know. Because basically you have Qualcomm and you have Exynos, right, which is used in like Europe or whatever. So yeah, I mean the impact of this issue, even though it is behind privileges, I mean this can hit tons of devices. So the impact there is still pretty high. But yeah, overall, lots of cool background information, not overburdening on the background info, but it feels like it really hit the sweet spot of providing info without, bombarding you with it. So, yeah. All right, we'll move on to Talos. Talos appears again this week. This vulnerability reports covers a use-after-free in Foxit Reader, which is a PDF reader. Because PDFs are broken with how powerful they are, readers commonly use a JavaScript engine, which is a really nice bug farm for exploiting them. And as you can guess, this vulnerability has to do with the JavaScript engine, particularly when it comes to how annotations are handled. So one of the things you can do in PDFs is set up these page handlers, page close handlers, so that when the page goes to get closed, it can execute your callback before exiting, and you can. That's presumably for any cleanup or whatever. Well, with the file attachment annotation, which is another thing the PDF supports, it'll prompt the user to select the file, which effectively blocks the main thread. So by adding a close handler and combining it with the annotation and switching the page, you can essentially get the backing object for that annotation freed while it's still being used when the dialog box gets closed.
I don't believe you need to add a close handler at all. I don't believe that's a user-provided callback. You can see that their code here that they actually provide for the crash. It's 4 lines, one of which is the function main, and the other one is the close bracket. So it's really just 2 lines of actual code that matter. And what happens is they do the this.pageNum equals 1, which changes your page. They're on page 0, presumably. I think they actually mentioned that, but yeah, changes the current page from 0 to 1, and then it adds that file attachment. So on the change from 0 to 1, that's when it's going to queue just the page close handler. So just in general, whatever code's there, that isn't a user-provided callback thing. That's just its own handler for like a page being closed or no longer visible. It changes the page, calls that, or queues up that handler on a separate thread. And then the file attachment in particular, because this is similar to if you've ever done like some JavaScript development and you've called like alert or dialog or prompt, you'll notice that any code that you have written after that function call doesn't get run until you actually close the dialog. It's the same thing with the file attachment here. It ends up blocking that main thread where it's called from. But that the close handler was set up, it was just queued up to be called elsewhere on a background thread. So that's where, the close handler gets called, but this page annotation is being added to the current this. So it's being added onto page 0 initially. The actual annotation itself impacts page 1, which they provide. But it gets, when page 0 is closing, it's going to see that annotation, access it, try and close it, and destroy it out from underneath the blocked main thread. But yeah, you don't have to set up any sort of close handler. That's unreal, or that's just how it kind of works in general. It's just the fact that the file attachment blocks on main for a while, long enough to let the close handler run and delete the annotation under it, or free the annotation under it.
Okay, sorry. The way I read it was, for some reason, I thought you were allowed to set that close handler, and that's they were abusing that. That said, when I was reading it and I saw those code snippets, I kind of noticed the same thing, that they didn't explicitly have that in there where they set up that close handler. So I was a little bit confused on that. So that kind of clarifies my confusion there. So yeah, my bad. So yeah, the close handler just kind of runs on its own. It's not something you define. Okay.
Yeah, and to be clear, also they do get code execution because there are vtables with this object. So with the use-after-free, you do get control flow hijacking.
We talk about vtables a lot in this episode, huh?
Well, I mean, it's pretty fundamental to C++ code.
Yeah, it's just Yeah, I feel like we're talking about more like issues in C++ targets than normal. Anyway, yeah, I mean, as is the case with Talos, we get a little bit of background info on the issue, some snippets of like the crash, but um, yeah, it doesn't go too deep into the exploit process. They focus more on the vuln research angle. All right, so up next we have a very cool target that we've never really seen on the show before. It's a software-based rasterizer for 3D graphics. So we've covered some graphics drivers before, but this article is around llvmpipe from Mesa. So it's something you can use on Linux if you don't have a GPU. So it's cool to see because I did some preliminary looking into using this driver for some PS4 work, actually. Just because of the fact that like the PS4 GPU is so annoying to interact with that it was like, can we do software-based rendering? So we did do some preliminary investigations into using llvmpipe. So yeah, it's cool to be able to cover an issue in it. Anyway, in this article, they talk about a stack-based out-of-bounds write when doing shader translation. When parsing the shader, WebGL will take any data structures that are used in that shader and it just places it on the stack. It doesn't like allocate it in the heap or anything like that, which in normal cases is probably fine. A shader shouldn't be using like a ton of space. But what happens when it does, right? What happens when something is placed on there that's so large that it exceeds the size of the stack? Well, you end up with an issue where you could hit adjacent stack pages, or in the initial case here, an adjacent guard page. So the issue is fairly straightforward. The exploit, though, they had to take care to work around a few issues. Like I said, the initial problem they had was that the shader that triggered the bug wouldn't work because you would end up hitting a guard page when it tried to initialize the array, which it does automatically at time of allocation. So that would trigger a crash when it went to write 0 there, which isn't really too useful at all. So they had to craft a shader file in a manner that'll cause the array initialization to be skipped. Which they do by gating it behind an if statement and carefully choosing offsets that'll get control over the instruction pointer or the program counter. They did have some additional issues as well.
So they gate. I think it's really important to talk about why they end up gating it.
Okay.
And that's, well, at least I thought this was a really interesting part of their attack was what ends up happening is that 0 initialization that Spectre mentioned. That happens when so actually I should mention this shader code gets translated into more of a C code and they inject the initialization, which is the for loop, just iterates over the entire array, setting everything to 0. It only does that initialization though on the declaration of the array, which is what gets gated off, but it actually creates a stack space for it and sets up the stack frame for such a large array. Right at the start of the function, it doesn't change the stack frame size while the function goes. So it's like old school C in that way. So because of that, that's why by gating it off, they're able to basically make so that initialization never happens, but it's still taking up all the space on the stack. So another variable can exist afterwards, after it on the stack and actually be kind of in this other frame. So I just thought that was kind of a cool trick to go about it. So I wanted to call that out.
Yeah, for sure. They did have some additional problems, though. Like, they had to work around AVX being used to perform the writes. Obviously, when you're doing software-based rasterization, you have to be very performant. So, yeah, AVX is a way to quickly write a lot of data. That, I believe, they fixed by using a vertex shader instead of a fragment shader. Now, I'm not a game dev, so I'm a little bit out of my area here, but I believe like fragment shaders are used for doing like the color information, like the color bitmaps, and I think the vertex shaders are used for drawing the like lines of the objects, the object frames, I guess. So because of the way those two different shaders types were handled, by just switching the type of shader they were using, they were able to get around AVX being a problem. But yeah, like I never really expected to find a blog post that talked about hitting something like llvmpipe and exploiting through shaders. It's a very interesting attack surface that I just haven't really seen much about, but it's one that you think you would think about pretty easily because, I mean, shaders are a language, right? It's not as powerful as a language as like JavaScript or something, like when you hit browsers, but it is something that gets parsed and translated into doing like memory operations. So it totally makes sense as an attack surface. It's just weird to me that I haven't seen anything or any blog posts that talk about it until now. Maybe that's just because it's kind of an obscure area and it hasn't popped up on my radar. But yeah, I mean, at least personally, this was a first for me to see.
Yeah, I thought it was an interesting post kind of for that reason. I think we've talked about one, maybe not in the shader, but we have talked about another GPU vulnerability, I think, before. I guess technically this isn't GPU because of where it is, but they do call out that actually getting RC and useful RC would be difficult because the process is running within a sandbox. And in this case, ASLR and getting an info leak, there's no clear way to get that with this bug.
Yeah, when you were talking about the previous GPU issues we covered, the one that comes to mind is like the Adreno GPU in Android. I think there was a Project Zero post on that. So that's another like cool post people should check out if they find GPUs fascinating. Just wanted to take from chat. Philip the Cat said vertex is for the data related to vertices, color, position, normal. Fragment is for how do I draw a pixel at 1010. Yeah, so I guess the fragment shaders are more for drawing like surfaces. Like if you had a cube, it would be more for the surfaces, where the vertexes are for the for like the edges and vertices and whatnot. All right, makes sense. Thanks for that clarification. But yeah, with that said, we'll move on to our last topic of the episode, which is a ZDI post. And it's a privilege escalation in Win32k. So Z, I'll let you take this one away because this was one that I didn't have time to get a thorough reading on today.
Yeah, and I thought, so we've actually talked about direct composition before. I feel like it was only a couple episodes ago. I should have actually taken note of where we talked about it. Do you happen to recall? Actually, I did take note of it. Episode 73. We have another direct composition. So, basic idea with direct composition, it was an API introduced Windows 8. The idea being you could send several commands over and basically buffer them or batch them together, making just the one call to process channel batch buffer, which would process several commands rather than needing to make them each in one command. They mentioned something about this being presented at CanSec West 2017, so... Oh no, I said Windows 8. For some reason I had in my head 2018, so never mind that. Anyway, vulnerability here. I could see some similarities with the last one we covered, but with this one, it basically comes down to in direct composition, you can create these tracker objects. They don't go into the details of what tracker objects really are, what they're tracking. I don't actually know because I haven't used this API, but you have tracker objects and you have a tracker binding manager or tracker binding manager, marshaller, or something. Long class name here, which makes it a little bit annoying to read. The binding manager will track pairs of the trackers. So it'll just have like a list of like tracker 1, tracker 2, and some ID to reference that tracking pair. And you can have multiple trackers being tracked by the binding manager. So the first vulnerability, this is actually a 2020 vulnerability, and then the issue discovered more recently in 2021 is a bypass for the fix. So I am going to talk about kind of the original vulnerability. And I should shout out a lot of background on direct composition here too, just on how it works in general. A lot better, I think, than the last post we covered on direct composition. So that is an area of interest, and it does seem like it's a bit of a bug farm right now. And this is running kernel privileges on Windows, so fairly useful. Or there's a kernel on a user side. It's running privilege though, so it is a worthwhile attack surface. So as I was saying, it will track basically tracker 1, tracker 2. It will track these pairs of trackers. Confusing myself with the language. One of the things that happens is that if you free a tracker that's being bound or is in one of these pairs, it'll free both of the trackers. That's kind of what the binding does. So when you free the one tracker, it frees the other, and it will free its entry from the actual binding manager itself. It's that freeing the entry in the binding manager that's kind of interesting. So what ends up happening is when you add a tracking pair, it'll of course kind of create this list or entry object, add the two trackers in there, give it a tracker ID, or give it an entry ID, sorry. And then it will go into each of the trackers and it'll set this single object, the binder manager object, or I think it's just binder_obj. And it'll point that over to its binder, so you can kind of reference back. When you free it, it'll use that reference to find its entry, find its partner, do anything like that. So where the vulnerability happens is in the fact that if you were to assign a tracker to multiple different binding managers, it only stores the reference to the one binding manager, and it'll overwrite kind of the old one thinking it's old. It doesn't actually do any check there to see what happened to the old one or if it's still valid. It'll just let you rebind it. So when you end up freeing it, the binding manager's entry, it only frees the one. It only frees it in the graphic they've got on screen here, tracking binder A and tracking binder B. If you free it on this side, on the B side, it only ends up freeing the entry on B and leaves a dangling pointer on A because it doesn't know about A. It doesn't know to even look at that binding manager to see what it should free. So that's basically what they take advantage of here, getting a use-after-free, because the first binder still stores a reference. In theory, you could also do multiple managers, like 3, 4, 5, and all of them will be left with dangling pointers, and just the one gets freed. They fix this effectively just by checking that binding object field that I mentioned. Just check if it's not null. And then if it is, or if it's not null, it'll go forward with actually adding it into the array. If it is null, if it is null, it'll add it into the array. If it's not null, it'll fail and, won't add it because it's already bound somewhere else. Makes sense as a fix. The issue is that I should have mentioned this earlier, but when you free it, it kind of does it in 2 stages. When you free the tracker, it will find its entry, it'll iterate over all of the tracker entries, the tracker list, and it will set the entry ID to 0. And then it calls this other function, clean up list items pending deletion. So it basically uses anything with an entry _ID of 0. It's saying those need to be deleted, and then this other function actually goes and does that deletion. So the way they were able to get around the patch was that they could actually trigger an update of the entry ID, because that is user provided. So they would just set the entry ID to 0, and that would end up triggering, you'll see on the code here, that will end up triggering this check to pass, which effectively ends up calling not the entire delete that we just saw earlier, but it'll end up calling the remove binding manager reference. So it'll end up doing half of the process. It'll still remove the binding manager reference, or it'll free the binding object that I mentioned, the one that's actually getting checked by the patch. It'll free that, set it to null, but it won't free the underlying object yet. Under a normal circumstance, that's going to be done, or it'll be called after this. But because we're kind of just setting the object to ID 0, which is the edge case or like a special value internally, it'll get it freed and you'll have access to the original vulnerability again. And they don't really go into the full exploitation of this. It's just kind of that vulnerability. You do have, it calls a function on this. So again, you're able to get a function call. So you do have EIP or RIP control from it, but they don't go into the actual chain afterwards.
Yeah, it's funny, not really related to what you were talking about, but you were just scrolling through on the stream, and I saw the one function name was so long that it was actually overflowing the blog area that they have there. So gotta love 132K and the long function names.
There's actually, I think, 2 that go. Yeah, this one, fortunately, people watching can't see the length of this one. But there is one that's a direct composition, see interaction tracker, binder manager, marshaller, remove binding manager, reference room tracker if necessary.
That's so outrageous how long it is.
Yeah, actually, on some scale. So when I was actually reading this, I on kind of the way it scaled the website, it actually trimmed those off, so I didn't even see those extra characters. But when you're in this sort of browser view, it's fine. But it is a bug with their site if you have too long of a class name, I guess.
Win32k hacking back ZDI's blog.
I mean, it feels like a lot of Windows things have these like large names.
Yeah, it's kind of the Microsoft philosophy to keep everything verbose.
And kind of like a little bit of Hungarian notation. I see that C, and I know with a lot of .NET stuff, seeing the Hungarian notation.
Yeah. Yeah, it's always nice to see those bypasses though of when they attempt an initial fix and it just doesn't land.
Yeah, they actually mentioned that Project Zero had a statement that I thought maybe it was a different post. Well, I guess I can't find it in here. It might have been a different post. That just mentioned like 25% of patches don't fully patch 25% of O days have incomplete patches.
That's interesting. I don't remember. We mustn't have covered that on the
I don't know.
show, did we?
I thought I saw it when I was doing notes for this episode. I thought it was here in this episode, but I obviously don't see it.
Oh, fair enough. Yeah,
so,
that seems higher than I would have expected. That's why I was thinking like I feel like I would have remembered that figure.
Since I'm not seeing it here in this post, it very well might not have existed. So let's not treat it as an actual quote anymore.
Might be in the ether.
I might be crazy.
Just like my my 32-bit and 64-bit truncation issue.
We both have our craziness this episode.
Yeah, something in the air. With that said, we'll move into our shout-out section. So Z, I know you have a shout-out. I'll let you go into that first, and then I'll get into mine.
Yeah, so I had one shout-out here. It's kind of a big one here, but 21 nails, multiple vulnerabilities in Exim. We've talked about vulnerabilities in Exim before. I don't think it was Qualys who found them last time. Or not, is it Qualys? Yeah, Qualys did it this time. But 21 vulnerabilities is a lot of vulnerabilities. Some of them are kind of interesting, actually. Like there's some symlink abuse, using new line injection to get remote code execution, stack-based buffer overflow just by having a long file name. There's heap overflow. A lot of vulnerabilities in here, a lot of really quick write-ups of them. Because there's so many, we weren't going to cover all of them. I figured I'd just leave it as a shout-out here.
Yeah, I mean, 21, that is a lot, as you so aptly put. So I'll get into my shout-out. This one is one that I recently saw on IRC. It's a topic about bypassing APPROTECT on NRF52 SOCs, and that was with the goal of re-enabling the serial wire debug interface. It focuses on that device, but it talks quite a bit about glitching, which is something that I really love in terms of like how it works, and I'm very interested in it, but I'm not very experienced in, so I wouldn't really be comfortable covering it as a topic because I don't do like hardware hacking, but I know like for a lot of people out there, hardware is kind of like this mystical thing where people don't really know how it works. Yeah, it's dark magic trying to hack them, do hardware hacking. So whenever I see a blog post that tries to cover it and covers it in a way that's accessible, I want to shout it out. So yeah, if you're interested in hardware stuff, I'd recommend checking out this blog post. I've seen some other people that have commented on it. It is a little bit older. It's from June of 2020, so it's not like super new or anything, but it was new to me, so I wanted to bring it up. But yeah, I've seen like some other people talking about it, saying it gives like a nice introduction to voltage glitching. So yeah, if that's your thing, definitely worth checking out. But
I will actually add one more shout out, and that's just the fact that we did do a video last week, a discussion video about Capture the Flag. So after our podcast regarding the Capture the Flag content, after that bit of discussion, we decided to dive into it a little bit deeper, and just talk about kind of some of the frustration, some of the meta when it comes to Capture the Flag. and just some of her overall thoughts on like challenge design, things like that. So you guys can definitely check that out also.
Yeah, good plug. I will quickly take from chat. Thanks, 1342 said his follow-up with the Logitech mouse is really good also. Okay, so I didn't know about that one. I'll have to give it a read. But yeah, for those who are interested in the last shadow, that's another point that I thought I'd highlight really quick before we bounce out of here. But yeah, with that said, that's all of our topics for this week. Thanks to everyone who tuned in. You can catch the VODs on Twitch or YouTube, as well as Anchor 24 hours after the podcast. Follow us on Twitter and join the Discord for notifications of when we go live and when we put out new content. Both links can be found in the chat and in the description of the video. Once again, we will be taking our summer break on May 24th. So May 24th will be our last episode until September 6th when we return. That said, we will be back again next week at the usual time, 3 p.m. Eastern, 12 p.m. Pacific, and we will see you all then.